Everybody. Okay, guys, so acid-base lesson 7, titration curves. Nice short lesson today, which is going to be nice. Okay, so I'm just going to crack straight on. Let's share my screen. So acid-base lesson 7, titration curves. There we go. Get rid of that. There we go. I'll make my chat appear. There it is. Oh, Jack. You'll get there one day, Jack. Okay, let's go. Let's go. I'll switch over. Najma, hello. Switch over to my, clip cam not connected. Uh-oh. I think I'm plugging in the wrong thing there. I definitely am. Oh boy. Let's try that again. There we go. Woo! There. Okay, guys. Isn't it very early for you? It's like 10 o'clock. No, it's all right. It's all right. Right. Okay, guys. I think everyone. Oh no! I've just slept. I've just pressed the button on my laptop. Oh no! Sorry about that, folks. I'm hoping it's all still there. Should be. Woo! There we go. Sorry about that. Right. So today's lesson, acid-base theory, lesson 7, titration curves. 2 learning objectives. Keeping it simple today, guys. So I need you to know the curve shape. So let's lob these into our books. Learning objectives. No titration curve. Whoops. Titration curve shape. And then the next one is understand the shape. It would also be, if anything, to be able to explain it. That could also be another one. Yeah, but we'll go through these now. Okay, so I'm finishing A2 and I'm here, and here I am at 5 a.m. watching your videos. Just came to show my support. Love what you do, sir. Have a great day. Oh, thank you so much. That is such a nice thing. You're just finishing A2, are you? I really hope that my webinars have been useful for you. So it's not sharing your screen. Share. Thank you, Jack. There we go. Is that better, Jack? Is it all working now? So nice that Najma, I don't know if I'm saying that right. I'm really glad I helped Snapchat. Naja. I'm making failing. What a failure. I'm so sorry. Hassan. Yeah, fab. Let's crack on. So it's you. Well, by the way, in terms for you, for your A2, this of course acid-base theory ties in heavily into A2 when you do acid-base properly. So you'll have a much better understanding of what this curve is about. Najma. Hey. Okay, so what we need to do is we need to have a look at this. So what we're going to do, titration curve shape. So how do we actually monitor this? So what we do is we set up a burette, yeah, and we fill the burette. Let's fill the burette with sodium hydroxide. And then what we're then going to do is we're going to put in a beaker. In a beaker, we now add our acid, our HCl. And what we then have is a pH probe. So this here is a pH probe. Now, what you also need to make sure you have is a stirrer. Yeah, so this has to be stirred. So we could add like a little, there you go, a stir bar, which will rotate. Love a coffee. Coffee would be lovely. So this is a stir bar. This is actually quite important for when you're doing titration curves. And what we're now going to do is we're now going to we're going to create a graph of what happens to the pH as I add the sodium hydroxide to it. Hi, Zakaria. Lovely to see you. Thanks for coming along. One of my best subscribers there who's always here to give us support. Thank you so much for being here. It's nice to see you. So we've got vol of sodium hydroxide, vol of NaOH here in centimeters cubed, and then we've got the pH on this axis. So at the beginning, we've got our pH probe. This goes off to a data logger, by the way. Yeah, this is a little laptop. This is a laptop, loads of keys. Yeah, to our data logger. Data. Data logger. And what we're going to do is we're going to add sodium hydroxide. We're going to monitor the pH. So what now happens is, and I'll explain what's happening. The first thing is when I've got 0, I'm going to add this in 1 centimeter cubed. I'm going to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Doesn't really matter. The pH is going to start at 0 and end at 14. And what we know is that strong acids tend to start off at pH 1. They're low. Yeah, strong acids. So our HCl, I'm going to do pH 1. So that's going to be 7. So I need to make sure that I do some lines here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Look at that. That was awesome. Well done, Mr. Duncan. It's good. Right, now what's going to happen is we're going to be starting off in acidic conditions. Right down there at pH 1. We haven't added any sodium hydroxide. Let's look at why that is. The reason for this is let's look at what the beaker now looks like. The beaker currently looks like this. And it has loads and loads of H pluses floating around. This is what hydrochloric acid looks like, by the way. Yeah, H plus, Cl minus. Let's add some more. Let's do 6 in total. I think 6 is a good number for this particular picture. And then Cl minuses. I like it. Need 6 Cl minuses. There we go. I like it. So that's what the beaker currently looks like. And our pH probe, what it's doing is it is picking up those H pluses. It's actually able to see them. By the way, if you're interested in how a pH probe works, it uses infrared light. It's using IR. Najma, you'll know this. It's actually picking up the OH bond in H3O plus. If you're interested, this is beyond GCSE, folks. It's picking up the fact that you've actually formed an additional bond. That's actually what H plus is, but don't worry about it, guys. You don't really need to know that. But it's picking it up using infrared light. Yeah, so it's detecting the H pluses. So everyone here would agree, at the beginning, at the start, the probe is detecting 6 H pluses. Let's just call that pH 1. Yeah. Now, what now happens is, I'm now going to add a base to this. Yeah. We're now going to add our base. Now, we know that bases are alkali. Yeah. So we're going to add our base a bit at a time. And what we now get is a rather interesting thing. Now, so at the beginning, we got 6. I now add sodium hydroxide, an OH minus ion. Yeah. We know that. This is just a reminder, a nota bene. H plus is what makes an acid an acid. Yeah, H plus acid, proton donor. Yeah, acids are proton donors. And we remember that a proton is a H plus because it's lost its electron. And that OH minus is your base. Yeah, and this is a proton acceptor. Yeah, acceptor. We know these. It's just nice to remind us. So the OH minus, what you can now see is the OH minus is going to react with one of the H pluses, and it's going to become water. So these two now react together, and they now disappear from the situation. And what you realize is when they vanish to become water, what you now realize is there is still loads and loads of H pluses floating around. There's still 5 of them left, which means it's still acid. So I now realize that the pH is going to increase, but it's not going to increase by much because I still have loads and loads of H pluses still there, and the base is no longer there. It's gone. It's been turned into water, and water doesn't actually have a huge bearing on pH changes. In order to change a pH by dilution, it's incredibly difficult. Yeah. So The first reaction goes in and becomes water. We now add a second drop of water. Look what happens. Sorry, a second drop of OH minus. The second OH minus cancels out another H plus, and that now becomes water. Yeah, that now also becomes water. What you realize is there are still loads of H pluses, which means it's still very acidic. It's going up a little bit because it's becoming more dilute, but it's not changing by much. Let's keep going. We add another drop of OH minus. Yeah, OH minus. And this one now cancels out this one. And they now become water. So they now become water as well. Once again, there are still loads of H pluses floating around. The pH does increase, but not by much. We get to another one. Yeah, we're going to add another OH minus. We add another centimeter of sodium hydroxide. This one cancels out this one, and they now become water. And what you realize is there are still H pluses left in the beaker. There is still acid left in the beaker. Yeah? And so the pH does increase, but not by much. You're about to see why it goes vertical in a second, folks. Right, I add another one. You add another OH minus. And that one reacts with H plus. Let's write the equation of what's happening. The H plus from the acid reacts with the OH minus from the base. By the way, I should actually color code this as well, because we know that an alkali is going to be purple OH minus with universal indicator. Yeah. And they're forming water, which is neutral, which is why it doesn't seem to change the pH. It's not really doing much because water isn't a base or an acid itself. So it's becoming neutral. This is called the ionic equation for those people. Yeah. This is the ionic equation for neutralization. For neutralization. There we go. So that one now becomes water as well. Boom, it's gone. Water. And we still have H plus in the beaker. It is still there. It is still acid. But all of a sudden, we're now down to 1. And now this time, only 1 left. Just 1 left. Now we finally see a bit of a change. We've got 1 left. 1 left. But now, look what's about to happen. I now add another sodium hydroxide. And what now happens is all the acid vanishes. And now all we have left in the beaker is water and Cl minus ions. And Cl minus ions are salt. They don't affect pH at all. So what that means, I have now just suddenly reached pH 7. All of a sudden, my graph skyrockets. Boom. It suddenly just shot up to 7. And now I'm going to add 1 more drop of sodium hydroxide. 1 more drop. And what you now realize is I'm now an alkali and the pH skyrockets. We've now just gone from acid. All of a sudden, it's jumped up to pH right up 7, right up here. And then as we add more OH minuses, yeah, it becomes a little bit more basic, but you're already high. So the graph is a very odd graph. There you go. So we get a very unusual graph. We get what's called a titration curve. So we have the acid region, the acidic region at the beginning, acidic region, and then we suddenly get this vertical region. And then, by the way, the region here is actually vertical. The reason being is if you actually monitor the pH closely enough, if we were to do fractions in here, instead of doing 1 centimeter, if we did this drop by drop, the graph actually becomes completely vertical. If you take loads more readings, it actually has what's called a vertical region, and it jumps. The reason being is because you're going acid, 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 neutral, boom. and then jumps up to base. It suddenly goes whoosh and skyrockets, and you get this solid vertical region of the graph. And this is actually where the indicators have to change color. Just to tell you, by the way, that's neutral is pH 7, and it is dead in the middle of the vertical region. If you ever get to do one of these graphs in the exams, yeah, there's your vertical region, and neutral, or for Najma, that is called the equivalence point. The true equivalence point, the true neutral point, is the middle of the vertical region. Morning, Nita. So nice to see you. Thanks for coming. So we get this rather cool graph, and they do like asking them. So first of all, know your shape. We know this. It's a really cool shape. Yeah, it's an S, and then understand the shape, which we now do. So what I'm now going to do is I just want to bring this now to a couple of questions from exam papers. So let's have a look. See if I can track my ones. There you go. So there it is. So this is, I can't remember which paper this is from. This is Edexcel iGCSE. I can't remember which paper it comes from, but there's the titration curve. And it's so important that I teach this, because otherwise you'd see that and be like, what is going on? Why is that graph in chemistry so strange? Because chemistry doesn't have strange graphs. We only have 3 types of graphs. It's either straight or curved. Yeah, people are going to say, hang on a minute, you said 3. Because you could have straight lines through the origin or just positive correlations. Yeah. But anyway, so it says here, use the graph to answer these questions. What is the pH of the sodium hydroxide before any acid has been added? And you just go, it's 13. You just read off the graph where it starts. My laptop's really struggling here. Read off the graph at the beginning. Yeah. And I really want to be able to circle that. It's not letting me draw on it. So it would be 13. You're reading the graph straight off that point. It then says, what is the pH of the solution after 40 centimeters cubed? Well, you just once again, yeah, you just, it's not letting me draw on it. I could screenshot. You take 40, you draw your dotted. I'm actually going to screenshot that one. Yeah, no. Let's do full screen snip. There we go. So the reading at 40, you'd see, it would always say on the question, show how you found your answer on the graph. So you draw these dashy lines, yeah, using a ruler, and then you read off the pH. At the beginning, you read it off up here. It was pH 13 before any acid was added, not complicated. Yeah. Next question then states, what volume is needed to completely neutralize the sodium hydroxide? Right. To completely neutralize, you find pH 7. Yeah, I'll do another screenshot. So new screenshot. Mode full screen. Right, once again, I'm just trying, sorry, there you go. What volume was needed to neutralize it? You find pH 7, yeah, and you read it off. There's the vertical region, and then you read it off, and that was 25 centimeters cubed. Yes, this is not a complicated issue here, folks. But it has to be taught, because if you don't teach it, students make mistakes because of never seen an odd shape like this before in chemistry. Write the chemical equation for the reaction between sodium hydroxide and hydrochloric acid. That's nice and easy. HCl plus NaOH goes to sodium chloride and water. And then we're into calculations. I want to see if there's another graph. There's another burette reading. You know the tricks. Look, they're in the table. End is first, but start is on the left. You know, they always do this, don't they? We know these tricks. Yeah, I'm just looking for this. Naming your pieces of equipment. There's another burette reading. I'm just looking for another graph if there is one. It usually is. Oh, not in this booklet. Okay, so guys, that's actually the end of my lesson today. I don't want to waste your time, guys, and spend ages doing something I don't need to do. So I will post some graph questions. Let's stop screen share. There we go. I'll even bring it back to my normal camera, so you're not looking at my forehead. There we go. Guys, I will leave you be at this point. Yeah, I hope you guys have a really good day. It's only 20 minutes just looking at graphs, understanding why the shape is that it is, and being then to use the graph to be able to find pHs and volumes. Really straightforward for today. I could have actually gone a little bit further for the A for Najma, just to talk about the fact that the vertical region indicators have to change color inside that vertical region. If they change color before that bit, you're never in the neutral section. But otherwise, a nice, easy lesson today, guys. Go and have a nice rest of your day, and I'll see you all tomorrow to go through your homework sheet. I'll see you later, guys. See you later.